So from table 2.1, we could see there's a wide range of pKa values, and that just illustrates there's a tremendous difference in acidity between different compounds. And so one of the questions that you might have is, how are these differences explained? And so there's one large kind of governing rule here that says, look, anything that stabilizes the conjugate base which is, remember, A minus is a way that we sometimes show that, right? Makes the starting acid HA is sometimes how we show that, more acidic. So in this screencast, we're going to talk about 4 factors that affect the acidity of the acid. And these are elemental effects or element effects, inductive effects, resonance effects, and hybridization effects. Now, you will be asked to compare 2 acids, right, to figure out which one is more acidic. And so here are the steps to compare 2 acids. The very first thing you want to do is always draw the conjugate base, okay? Because we got to figure out what's going to stabilize that base, and it helps to visualize what's going on. Then you need to determine which conjugate base is more stable, okay? And then the more stable the conjugate base, the more acidic the acid, okay? So those are the steps that I would suggest going through. So let's look at, and we're going to look at these effects in order. So let's look at element effects first. And so we're gonna look at some comparisons here. So if we look at the pKa's for water and methane, which is CH4, the pKa for water here, if we look at table 2.1, is 14. And then the pKa for methane here, if we look at that, it's 50. Okay, and so the question that we have is why is water so much more acidic? Why does it have a lower pKa than methane does? Well, when we draw, so we go through the first step and we draw the conjugate base, and so we just have a loss of a proton for both of these. These are the 2 conjugate bases that we compare. And what we see here is that oxygen is more electronegative than carbon. And if you have a more electronegative atom, it more readily accommodates or stabilizes the negative charge. Whereas if an atom is more electropositive, it's less likely to stabilize that charge. And so what we find then is that H2O is a stronger acid than methane because OH minus is a more stable conjugate base than CH3 minus, okay? And so what we find then is, if we look at this trend across the periodic table, as you go across a row and you increase in electronegativity, you also increase acidity, right? So the acidity of an acid increases as the electronegativity increases. Across a row from left to right. Okay. Now, so maybe the burning question in your heart is, oh, great. We've looked at a row. It increases across a row. What about a column? Do we see that same trend with a column? And the answer to that is no, which is unfortunate. But we do see a trend with columns, right? So if we look at two acids, we've got hydrofluoric acid and hydrobromic acid, we see that the pKa of hydrobromic acid is -9. It is more acidic. HF is less acidic. When we draw the conjugate base for HF here, it's F minus, right? And then here we have Br minus with hydrobromic acid. When we look at this, HF is a much smaller atom than the bromine. The bromine is a lot larger anion, right? And so the fluorine's a smaller anion, the bromine's a larger anion. The fluorine is less stable. The bromine is more stable. And so what we can conclude from this is that, right, a positive or negative charge is stabilized when it is spread over a large volume, right? And so as we go down a column of the periodic table, size determines the acidity. Right? And so that, as I mentioned, that positive or negative charge is stabilized when it's spread over that larger volume. So because the bromine minus is larger than the F minus, the bromine minus is more stable because that negative charge is spread over a bigger area, right? So we can say then that, right, the acidity of an acid increases, right, down a column of the periodic table, right? So the acidity increases as the size of the atom increases, right? The other thing that this tells us is that size is more important in determining acidity than electronegativity. Okay. So those are the elemental effects, right? Size and electronegativity. Let's look at inductive effects. Now, an inductive effect is just, when we talk about this and want to define it, it's just the pull of electron density through sigma bonds caused by the difference in electronegativity between the atoms. Right? So more electronegative atoms generally stabilize regions of high electron density, right, by an electron withdrawing effect. So let's look at an example here. We have ethanol and we have 2,2,2 trifluoroethanol, okay? This is the stronger acid. Now, both of these have an oxygen atom. The acidic hydrogen here is shown in red. And so when we draw the conjugate base, we'd remove that proton. And so that would give us this guy. And then we've got that. Oop, nope, just kidding. This guy here. Right? And what we find is that these fluorines, right, withdraw electron density, and they can withdraw electron density over more than one bond. And so we withdraw that electron density, and so that stabilizes the charge on the oxygen, okay? So more electronegative atoms stabilize regions of high electron density, right? By this withdrawing inductive effect, right? And even so, the more electronegative atom and the closer it is to the site of the negative charge, the greater the effect. Right? So we see this because we see that this is a stronger acid because these fluorines withdraw electron density and it stabilizes this negative charge. Now, there are other things that can stabilize the negative charge, and one of those is resonance effects. Now, right, delocalization of charge through resonance influences this acidity, and we can see this through the example shown here. We have ethanol, which has a pKa of 16, and then we have acetic acid, and that's got a pKa of 48. And so to explain why, let's draw the conjugate bases. So we've drawn the conjugate base of ethanol a few times, but we're going to draw it again here. And then let's look at the conjugate base of acetic acid. What we find with acetic acid is that it has delocalized electrons. So here, the conjugate base of ethanol has localized electrons, and the conjugate base of acetic acid has delocalized electrons. So that means we can draw a resonance structure here. Those electrons go there, and that makes those electrons jump there. Remember, we're going to use a friendly double-headed arrow that looks like this. It's not an equilibrium arrow, And that tells us, that communicates to us that that is a resonant structure. And so now we can draw the resonance hybrid, right? So those are the contributors. Let's draw the hybrid. And what we see here is that spreading out of the charge stabilizes it. And so that makes this a stronger acid. Now, the last thing that we're talking about of the last four effects is hybridization. And what we find with hybridization is that the higher the percent of S character of the hybrid orbital, the more stable the conjugate base. And remember, if the conjugate base is more stable, it means it's a stronger acid. So let's look at some examples. If we look at ethane, ethylene, and acetylene, all of these have 2 carbons. The only difference is the hybridization. So if we review hybridization, we remember that this carbon is sp hybridized. This carbon is sp2 hybridized. It has 3 groups. And then this carbon here is sp3 hybridized. And what we see here is that when that acidic hydrogen from the carbon is removed to form the base, that as we increase the S character, then that stabilizes the base. So this is the most stable base, and so this is the most acidic compound when we compare these 3. Now, a lot of times what these questions are going to do is they're going to have you compare. So you've got to remember what you're really doing is you're going to compare 2, 3, 4 compounds. So I love summary tables. So this is a beautiful summary table that talks about each of the each of the effects, element, inductive, resonance, and hybridization, and then gives you an example of these. So this is great when you're going to answer some of these questions. Now, I have the steps written out for you on how to determine the relative acidity of the protons, in case you wanted to refer back to these. So the first step, after you write the conjugate base, is you need to identify the atom, right, that's bonded to the hydrogen, and then use the periodic trends to assign relative acidity. The most common HA bonds in organic chemistry are from a carbon-hydrogen bond, a nitrogen-hydrogen bond, and an oxygen-hydrogen bond. Those are going to be the ones that you see most often. Remember, acidity creases from left to right across a row, right? So that means that this is the most acidic, right, bond as we go across the row. And then hydrogen atoms bonded to carbon atoms are usually less acidic than hydrogen atoms bonded to any other heteroatom. So those are some good kind of rules as we look at this. Then, right, if the 2 hydrogen atoms in question are bonded to the same element, draw the conjugate bases and look for other points of difference. Are there electron withdrawing groups near? Is the conjugate base resonance stabilized, right? How's that conjugate base hybridized? So the element identity with size and electronegativity with size being the most important, and then these come next. So let's look at an example. So this example says, rank the following compounds in order of increasing acidity of their most acidic hydrogen atom. And so we are going to look for the hydrogen atom on heteroatoms. And so the acidic hydrogen atom that we're looking at is this one here, and then one of these 2, okay? And so when we draw the conjugate bases, we get these structures. Here, okay? And so when you look at this, you say, okay, hey, look, I'm looking at the atom that's got the negative charge. So we're comparing oxygen, oxygen, and nitrogen, okay? So what we see here is because the acidity increases from left to right, the OH bond here is going to be the most acidic, okay? This is more electronegative than nitrogen. So because oxygen is more electronegative than nitrogen, right? The compound with oxygen will be more acidic. Okay, now we have two of those, right? We've got two compounds with oxygen. Both A and B have that. But what we can go ahead and do is say, look, right? Compound C is the least acidic. Okay, then we can go and evaluate, right? A and B, right? And so the only difference between compounds A and B is the presence of the chlorine right there. Okay, so that's the only difference between them. The chlorine atom is going to stabilize the negative charge of the conjugate base. Right? Making it more acidic. Right? So when we order these, then we can say, hey, look, C is the least acidic because we're ordering them in order of their increasing acidity. So we go least acidic, then B is next, and then finally A, okay, because we've got those inductive effects. Try some of these problems in your syllabus. Remember, I've got a list of suggested practice problems for you to do. Try some of these problems, and if you have any questions, please feel free to stop by my office or send me an email and ask. I'm happy to help.